Okay, so what we want to do now is an example, and we want to see how we use Stokes' theorem. And I'm going to give you an example, and we're going to solve the same problem in 3 different ways. It's going to be kind of a practice thing. The first one is going to be, it's going to be a surface integral that we want to calculate. The first solution is going to be, we're just going to calculate the surface integral by definition of the surface integral. The second solution, we're going to use Gauss's theorem. And in the third solution, we're going to use Stokes' theorem. Okay, and we're hopefully going to get the same result in all 3 solutions. Okay, so here's the example. So example. So we have a field, F, and F is defined as follows: x plus y minus 4 in the I direction, plus 3xy in the j direction, plus 2xz plus z squared in the k direction. So this is our p of xyz, this is q of xyz, and this is r of xyz. And you can easily see that this field is C1 in the entire R3 space, right? Everything has continuous partial derivatives. Okay, now we need a surface. So S is going to be the surface, all the points x, y, z in R3 that satisfy z equals 4 minus x squared minus y squared, where z is non-negative. So this is the surface S. Usually it's good to be able to picture the surface, to decipher actually what it looks like. In this case, it's not hard. If you think about it for a minute, z equals x squared plus y squared is a paraboloid. And what we have here is minus that, so it's an upside-down paraboloid. And this 4 here means that its vertex is sitting at 0, 0, 4. So the picture of this thing is, let's take a color here, is a paraboloid sitting up here, whose base is a circle of radius 4 in okay, can you imagine that? Now, if for some reason that was too fast, if you can't see it easily, then you have to do it. If you want to be able to picture it, and usually it's helpful, then you have to just decipher it the way we did it back then. So you would set z equals 0. When z is 0, you get the circle x squared plus y squared equals 4. So that's a circle of radius 2 in the xy plane. When z equal, and it only has life when z is greater than or equal to 0. As you make z bigger and bigger, up to 4, at z equals 4, you get that xy have to be 0, so you get that point. And for all the other sections, you're just going to get circles of smaller radii. And then when you set x equals 0, you get a crying parabola with vertex at 4. So you can see that this is what you get. Okay? And it's just the surface, right? Just the surface. Points x, y, z that satisfy this are precisely this hat-shaped. Everybody good? Okay, so that's S. And what do we want to calculate? So find, so this is the example, the surface integral over the surface S dot ds of, you would guess F, but in this example we want to find the surface integral of the rotor, the curl of F, which is a different field. Okay, so this is the example, and we're going to solve it in 3 different ways, 3 different solutions. So the first solution is going to be just to calculate a direct calculation of the surface integral. Okay, so solution 1, direct calculation, no theorems, calculation. So what do I mean by direct calculation? I'm going to find, let's look at this again, I'm going to find the curl of f, plug it into the surface integral, and calculate the surface integral. We're going to need a parametrization of the surface, finding the normal, dot this with the normal, and so on. Clear? That's just calculating directly the surface integral. So the first thing I need to do is find the curl. What is the field that I want to plug into the surface integral? And this we did in a previous example. Okay, when we discussed the curl, in the clip where we introduced the curl, we took precisely this field and calculated the curl for it, and I left it here on the board. So this was it. Okay, so the curl of this field, this is how we calculate the curl. Everybody remember? What we get is 0 minus 2z, 3y minus 1. Okay, good? Okay, so this we're going to be able to erase in a minute. So a direct calculation. First of all, the curl of f equals 0 minus 2z and 3y minus 1. This is the field that I'm going to calculate the surface integral for. How do we calculate the surface integral? We need to parameterize the surface. So let's parameterize the surface. Parametrization of S. So S is this upside down paraboloid, and its axis of symmetry is the z-axis, right? So parametrizing it, a kind of simple way to parameterize it is to use to parameterize it based on what we call cylindrical coordinates, the cylindrical symmetry. So it's not change of variables, it's parameterizing it. So what is going to be the parametrization? X is going to be rho cosine theta. Y is going to be rho sine theta. And z, so if this is x and y and z was just z, that would be cylindrical coordinates for the entire R3 space, right? But I don't want that. I want only to capture points on the surface S, on this paraboloid, only points on this paraboloid. So points on this paraboloid, the rho and the theta have the liberty of being in all directions, and rho can go as far as 2, right? That's as far as it goes. So rho is going to be less than or equal to 2. Theta is going to be between 2 pi and 0. That restricts me to points above this circle. But what is the z? That's the key thing. Z has to relate to x and y by this formula. Do you agree? Z has to satisfy that z equals 4 minus x squared minus y squared. Those are points on this surface. Does everybody see that? So the parametrization is going to be z equals 4 minus x squared minus y squared, and x squared plus y squared is rho squared, so I get 4 minus rho squared. So this, along with this, is a parametrization precisely of points on this paraboloid. Yes?
If we put z equal to z, we are doing a change of variables?
If you're doing z equals z and not restricting, then you're just giving coordinates for the entire space. You're not capturing only these points.
It means a change of variables.
It's not a change of variables because you didn't change anything. Okay, you're just giving a set of coordinates to describe three-dimensional space, x, y, and z, where, okay, you can say that you changed from rho, theta, and z to x, y, and z. Okay, but there's no integrals yet. Okay, it would just be giving different coordinates for the entire space. That's not what we're looking for. We want to just be able to capture only the points on this paraboloid. Note that how many variables do we have here? How many parameters? 2, rho and theta. These are the ranges. This is the domain for rho and theta. This is the parameterization. Okay, parameterizations are kind of a bridge that you have to cross. Okay, you have to get used to them, and the only way to get used to them is practice a lot. Parameterize surfaces. You're riding the bus, parameterize the driver. I don't know. Just do it a lot till you get the feeling for it. Okay? But do it from afar. Don't come to him and say, let's parameterize your head here. Yes?
I just don't really understand like when you would use parameterization and when you would change variables. Like when.
Okay, so the question is, when do I use parameterization and when do I change variables? A long discussion of that we can do later. I don't want to do it now in the middle of this clip. Okay, just a quick answer. A parametrization of a surface is pizza. You want to only capture the points on the surface. Points of the form x, y, z, given as such, where rho and theta are between these two these bounds, are precisely and only the points on this surface. A point like the origin, which is not on the surface, right, cannot be prescribed like this. Do you agree? Because the origin has rho equal to 0, right? So it would be 0, 0, but z equals 4. If rho is 0, z is 4. Do you see that? So the only point with rho equals 0 on this surface would have to have z equals 4, and you would get this point. Do you see that? Not all points in three-dimensional space satisfy this. Only points on this surface. And you have to think about it. You have to start plugging in points like this point, and this point, and this point, and this point, and all kinds of points, and convince yourself that this is precisely capturing this surface. Okay? And it's very different than changing variables where you're just giving a different coordinate system for the entire space. Clear? Okay, if you need more, if you need a broader discussion, and many times this is a hard step to take, then we can discuss it later. Okay? Okay, so this is a parametrization of the surface S. What we need in order to calculate the surface integral is the normal. So what is the normal? I'm reminding you, the normal, so this is r of theta and rho. The normal is r, which r rho cross r theta. That's how we find the normal to a parametrization. So it's I, j, k, and then the component. So r theta, r rho is cosine theta, sine theta, and minus 2 rho. And r theta is minus rho sine theta, rho cosine theta, and 0. Do you agree? Good? Okay, and what we get, so in the I direction, I get minus 2 rho squared cosine theta. That's the I component. In the, sorry, not minus. It's minus minus, so this becomes a plus. Do you agree? Minus because it's this, and another minus because of this minus, so it's a plus. In the J component, I get, there's a minus sitting out there. This meets 0, so there's minus, 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 minus. It's again a plus, 4 minuses. 2 rho squared sine theta. And in the K component, I have rho cosine squared minus minus, so plus rho sine squared. So it's just rho cosine squared plus sine squared, so it's just rho. So this is the normal.
Wait, shouldn't it be rho cosine squared plus rho sine squared? Shouldn't it be rho? Oh, yeah.
He asked the question, shouldn't it be Yeah, good, good. Okay, so this is the normal, but I answered it very, very in a convincing way, didn't I? See, I'm a good teacher, huh? Okay, good? Everybody good? Okay, so this is the normal. What are we doing? So we want to calculate the surface integral of this field over this surface. Okay? How do we calculate a surface integral of a field over a surface? We do the field, calculated on the parametrization, dot the normal, calculated over the range of the parameters. So what we want, so the double or the surface integral over S of the rotor of the curl of F dot ds equals, we need to take the double integral over the space of the parametrization, so from 0 to 2 d rho of the integral from 0 to 2 pi d theta of f dot n. F is now this, so it's this. So we need this calculated on the parametrization. So we have 0 for the first coordinate, minus 2z, minus 2 times this. Everybody with me? Minus 2 times z, so it's minus 8 minus minus plus 2 rho squared. This is the second component of the field we're looking at on the surface. And then 3y minus 1. 3 rho sine theta minus 1. This is f calculated on the surface. Everybody with me? Dot the normal. This. Dot the normal. 2 rho squared cosine theta, 2 rho squared sine theta, rho. And then there was d theta, d rho. This is how we calculate a surface integral. This is the direct calculation. So this is the field we're looking at, calculated on the surface, and this is the normal. Now we just have to open all this long expression. Unfortunately, it's going to turn out to be very easy to calculate. So let's see how we do this. So first of all, 0 meets this thing. That's gone, right? And then I have to multiply minus 8 plus 2 rho squared times 2 rho squared sine theta plus rho times 3 rho sine theta minus 1. So let's see what I get. So tell me if you agree. I'm just going to write it here. From 0 to 2 pi, and then from, which one did we put outside? Doesn't matter. 0 to 2 of, so what I got is 4 rho to the power 4 sine theta minus 16 rho squared sine theta plus 3 rho squared sine theta minus rho. That's what I got. D theta d rho. So let's see. Minus 8 times 2 rho squared sine theta is this thing. And then plus 2 rho squared times 2 rho squared. So that's this thing. Then rho times 3 rho sine theta is this. And then rho times minus 1. Good. Everybody with me? Clear how I got it? Now we have to start calculating. And it looks like it might be more complicated than it really is. But in fact, 3 of these expressions cancel out. Because we're doing here an integral of sine theta, d theta, between 0 and 2 pi. Do you see that? The antiderivative is going to be cosine theta, plus or minus some coefficient, who cares? Evaluated at 2 pi, minus evaluated at 0. but they're equal. Cosine at 2 pi and cosine at 0 are equal. One is with a minus sign. They're going to vanish. Do you agree that this is going to be 0, this is going to be 0, and this is going to be 0? Does everybody see why? Okay? If you don't, then to be on the safe side, just do it. Okay? It's an extra step of writing cosine theta between the bound, plugging in the bounds, and you're just going to see that they vanish. Okay? So all I'm left with, in fact, is the integral from 0 to 2 times the integral from 0 to 2 pi. I didn't calculate it. I didn't take any step. I just looked into the future and noticed that these are going to be 0, and therefore I'm not going to calculate them. That's what I did. Of, let's put the minus out here, rho d theta d rho. So it's minus rho can actually move out, so I'm going to get 2 pi from the integral d theta, and then I'm going to get rho squared divided by 2 evaluated between 0 and 2. So I get 2 squared is 4, divided by 2 is 2, times minus 2 pi, I get minus 4 pi. Okay? So this is a direct question.
Does what you used to cancel out sine, would that also work for cosine?
It would work for this. I would recommend not to write things like this on an exam, for example, unless you're completely certain of what you're doing. Okay? What I did is I was a prophet. Okay? I looked at what's the next step going to be. The next step is going to be to find the antiderivative. The antiderivative of sine is cosine, up to a scalar multiple. Okay? Cosine between 0 and 2 pi is going to vanish. If it were cosine, the antiderivative would be sine. Same argument. Between 0 and 2 pi. If it were between 0 and pi, it wouldn't. Okay? And it's ad hoc. It works for this because it's sine and because it's between 0 and 2 pi. Okay? If it were sine squared, you would have to think. Okay? It's not that every time you see a sine, you can cross it out. That would be wrong. Okay. Let's do the second solution. So the second solution, question?
Yeah. How did you know in the normal to cross our rho like first and then afterwards rho theta? Will it change with the minus? No?
Yeah, we discussed that. When you do a parametrization, all that matters is that you have to be consistent with the data of the problem. Okay. So in this case, I don't think we even wrote. We should have. What direction is the normal? Okay, so in fact, it's a good question. Okay, the correct answer would be, in the original problem, we should have stated which direction we want the normal on S to be. And in fact, because of the next solutions, I'm actually going to want the normal to point outwards. Okay, and then when you do the parametrization, you have to check that what you got is consistent with the direction that you wanted for the normal. So you can like choose a point, calculate the normal at that point, and see if it points in the direction you wanted. Okay, so that would be the accurate answer. Okay, good. So the answer was minus 4 pi. Let's do solution 2. Now, notice that we worked. Okay, there were some things to calculate along the way. In the next two solutions, they're going to look shorter, but part of it is because I'm going to use things that we already calculated. Okay, so there's kind of a conservation of work law here. It always requires some work. Okay, so solution 2, let's use Gauss's theorem. So how do we use Gauss's theorem? Remember what Gauss's theorem said. Gauss's theorem started with, if you have a closed surface, right? Bounding region V. Okay, so solution 2, Gauss. But this surface is not closed. It's the upside down paraboloid. It's definitely not a closed surface. It's an open surface. I can stick my hand in there, right? So how do we use Gauss's theorem? It looks like a trick, but it's a standard trick. We're going to close the surface. Okay, so take our surface S, here it is. Let's start with this and then add this. So here's our surface S. It was this thing, right? This is our surface S. It's not a closed surface. It's not a closed surface. It's an open surface. Let's close it. How do I close it? I'm going to add down here the disk in the xy plane from the bottom. Let's call this disk S1. And when I add S1, what I get is a closed surface. Do you agree? Okay, now it's closed. So S union with S1 is a closed surface. It's piecewise smooth. It's comprised of two smooth surfaces. Okay. The normal is going to point outwards. So let's assume that the normal on S is pointing outwards. I'm going to take the normal on S1 to point downwards. Therefore, the normal on the S union S1 is pointing outwards, right? And now I can use Gauss. So, by Gauss's theorem, the surface integral on the closed surface S union S1 of the field that I'm looking at, the field that I was interested in was the rotor, equals, note that this is not what I want to calculate. What I want to calculate is this integral only on S, not on S union S1, right? I'm going to calculate this and then subtract the calculation on S1. That's how I'm going to solve it. So this equals the triple integral over the inside, over the solid which lies inside this paraboloid bounded from the bottom. Let's call it V. So V is the inside of this thing, of the divergence of the field. The divergence of the field that's written there. Do you agree? This is Gauss's theorem. Everybody remember? So what I have to write here is the field that I'm interested in, the rotor. Clear? Now in this case, the reason that this solution is a good solution is because this is easy to calculate. In fact, it's very easy to calculate. It's 0. Why is it 0? Because we had one of the properties of the rotor, of the curl, was that the divergence of a curl is 0. Remember that property? Good? So this is 0 because we're integrating over the 0 function. This is a scalar function. The divergence of a curl is a scalar function. And in fact, it's the 0 function. So I don't care what the domain is anymore. It's just 0. Clear? Everybody? Now, this thing, on the other hand, this thing equals the surface integral over S of the field, in this case, the rotor of F, plus the surface integral over S1 of the rotor of F. And we just found that their sum is 0. Do you agree? So the upshot is, we wanted to calculate this. This is the problem, the original problem. Look back here a second. This is the original problem, right? What we found is that if we add this disk on the bottom, S1, the sum is 0. Therefore, this equals minus this. Good? So therefore, and I'm going to move on to the next board. Therefore, the integral we're interested in over S equals minus the integral over S1 of the rotor. And we're going to calculate this, and this is much easier to calculate because the surface here is just a disk in the xy plane. The normal is just 0, 0, 1. It's very easy to calculate this. Do you agree? Okay. So this looks like a very tricky sort of solution. How did I think of closing the surface and doing... It's standard. It's kind of a standard thing to do, to use Gauss for open surfaces by closing them and subtracting what you closed by. Okay? So it's a standard approach. So let's calculate this. What's the answer going to be, by the way? Minus 4 pi, if we're doing it correctly. What? It should be the same thing, right? Okay, so let's see what we get. So this equals the integral over the domain. S1 is just the disk. S1 is x squared plus y squared is less than or equal to 4. Do you agree that this is S1? Right? And dx dy, I'm parametrizing S1 just by x and y. So it's dx dy. Now I need to plug in the rotor dot the normal. What was the rotor? What was the curl of f? I'll tell you, because we calculated only like 15 times, except I didn't write it here. It was 0, minus 2z, and 3y minus 1. This was the rotor. And dot the normal. What was the normal? It's not 0, 0, 1. Almost. Right. 0, 0, minus 1. And this shouldn't be z. This should be, we're calculating it over the surface. So this is in fact 0 as well. Do you understand why I replaced this by a 0? Because this was minus 2z. It was the component, the j component of the rotor was minus 2z, but I'm calculating it on the surface. The surface now doesn't have a z component. The z component is 0. It's the disk in the xy plane. So this is 0. Okay? Wait 1 second. So this is what I need to calculate. Okay? Question?
Shouldn't it be 0, 0, 1 because you're saying the minus S1? Actually, you have a minus.
No, no, no. This, oh, okay. This minus, I left out. This minus is because of the arguments that preceded. That this integral plus this equals 0, so this equals minus this. And this minus is because of the normal. We chose the normal to point downward in order for the surface to be closed with an outwards pointing normal, because those were the condition in order for Gauss's theorem to hold. Okay? So this is what we get. So now let's calculate it. Let's calculate it. So I get the double integral of, these two minuses indeed can cancel. So I get 3y minus 1 dx dy over this disk. This is the integral that we want to calculate. And now how do I calculate an integral over a domain which is rather circle-ish? Right, change variables of a double integral to polar coordinates, right? So I'm changing variables now. Now I'm doing change of variables. And I get the integral from 0 to 2 dr of the integral from 0 to 2 pi d theta of y is r sine theta. So I have 3r sine theta minus 1 times the Jacobian r. Now I did a change of variables to this I wanted here. Now I did a change of variables to polar coordinates in R2. This was a double integral. Clear? And now I want to calculate this double integral. So what do I get? I get, oh boy. So I get the integral, I can do the same trick. Yay. This is this part has an integral of sine theta between 0 and 2 pi. This is going to vanish. Okay, because of the sine theta between 0 and 2 pi. So what's left is the integral from 0 to 2, the integral of 0 to 2 pi of minus r d theta dr. And integrating d theta would introduce 2 pi. This minus is going to be a minus, and this is going to be r squared over 2, and we're going to get minus 4 pi. Questions? Yes?
I know that in this case it's better to do the change of variables, okay? But like, in case we wanted to do like the parametrization, can we? Or like...
That discussion will continue later, okay? Don't try pulling me again every example, every clip to answer why is parametrization different than change of variables, okay? If you still need more explanations about that, I'll be happy to answer them afterwards, okay? Here it's just a standard change of variables for a double integral in dxy coordinates to the r theta coordinates. That's all that we did here. Yes? In order to use Gauss's theorem, the conditions for Gauss's theorem were that the normal has to point outwards. Outwards. So we closed the surface. The surface was an open surface. We closed it. Now it's a closed surface. We want the normal pointing outwards. So on the bottom, in order for it to be outwards, it has to point to the bottom, downwards. Clear? Those were the conditions of Gauss. Okay, so it looks like this is, again, something kind of original, but there's nothing original about it. It's a standard way of solving surface integrals using Gauss by closing the surface. Okay. Solution 3. So the title of this clip was using Stokes' theorem. So how about a solution involving Stokes' theorem? That's what we're going to do. And intentionally, I wanted to do this example and solve it in 3 different ways because we're accumulating knowledge here, and it's important to see how everything the interplay between everything. So solution 3 is going to use Stokes. The reason that it makes sense to use Stokes in this case is only because the field that we're interested in integrating over the surface is not f itself, but the curl of f. So remember the original problem. We want to find the surface integral of the curl. That was the original problem. And the surface integral of the curl, going one board back again, is precisely what we have in Stokes' theorem. Okay? So Stokes' theorem says if you want the surface integral of a curl of a function, of a field, it's the same as the line integral of the field itself over the boundary. Okay? So this is what I'm going to use. I'm going to pass from the surface integral of the curl to the integral of the original field over the boundary. What's the boundary? What's the boundary of our surface? The boundary is just the circle of radius 2. Do you see that? This is the boundary of our surface. This thing, this is gamma. This is the boundary in this case. Do you agree? The only thing we have to be careful about is how to orient gamma. This is in the back. So how are we going to orient gamma in order for it to comply with the conditions of Stokes? The normal we said is pointing upwards, outwards. So when we walk along gamma, either right-hand rule or left-hand rule, either way, the direction on gamma is going to be like this. So counterclockwise when you look at it from above. Clear? So this is the orientation on gamma. And now, using Stokes' theorem, so let's write it here, the integral we're interested in, the surface integral over the surface S of the curl equals, by Stokes' theorem, the line integral over the closed surface gamma of the original field dot dr. Is this clear? Okay. So how do we calculate a line integral? Right? Nothing comes for free. Now we need to calculate a line integral. Okay. How do we calculate a line integral over a curve? We parameterize the curve. Right? Parameterize the curve. Find r prime. R is going to be the parameterization. We need r prime, and we need to do f dot r prime. Remember that? That's how we calculate line integrals. So let's do that. So gamma is now circle x squared plus y squared equals 4. Not less than or equal, but equal. It's just the curve, right? So let's parameterize gamma. So parametrization of gamma. Gamma is the circle. Parametrization of gamma. So let's write it. Did I use t or theta? Theta. R of theta equals 2 cosine theta, 2 sine theta. And what is the z component? 0. It's sitting on the xy plane. So this is the parametrization of gamma. Note that there's only one parameter. It's a curve, right? Everybody good? What is r prime? R prime of theta. So it's minus 2 sine theta, 2 cosine theta, and 0. What is f? So we need the original f evaluated on gamma, right? That's what we're going to need for that line integral. F evaluated on gamma, not the rotor of f, f itself. So let's recall what f itself was. Here's f. This was the original f in this example. And we need to find it on gamma. So everywhere I see an x, I need to plug in 2 cosine theta. Everywhere I see a y, it's 2 sine theta. And everywhere I see a z, it's just 0. Do you agree? Okay. So what I get for f is x plus y minus 4. So 2 cosine theta minus 2 sine theta minus 4. That's x plus y. Y what? Plus x plus y minus 4. Then 3 times x times y. So 3 times 2 times 2 is 12 sine theta cosine theta. And then 2xz plus z squared. So 0 for the k component of f on the curve gamma. Clear? Now I have to do, so I'm going back here, this equals the integral over the parameters. In the parametrization is this, where theta ranges between 0 and 2 pi, because it's the entire circle. So I'm integrating from 0 to 2 pi d theta. And here inside, I have to do f dot r prime. This dot this. Do you agree? Okay. So let's save a line of writing, of copying this and putting a dot and writing this, and let's just do it. So this dot this. So what do I get? I get here minus 4 cosine theta sine theta. I'm not going to have space either way, so we're going to have to continue on the next board. So let's just write here the integral from 0 to 2 pi f dot r dot of theta d theta. Okay, that's what I need, right? So let's write it here. What are we going to get? Good. Minus 4 pi. Okay. So let's write it. Now that we don't have it on the same board, we're not going to be lazy. So the integral from 0 to 2 pi of 2 cosine theta plus 2 sine theta minus 4, 12 sine theta cosine theta and 0 dot r prime minus 2 sine theta 2 cosine theta and 0 d theta. This is what we want to calculate. It's a calc 1 integral in the variable theta, right? And now we're going to have to multiply things, but hopefully there we're going to have some antiderivative arguments of things canceling out between 0 and 2 pi without working too hard. So let's see what we get. We have 2 cosine theta times minus 2 sine theta. So it's minus 4 sine theta cosine theta plus another minus 4 sine theta squared minus, so plus 8 sine theta. That was these three terms times this. And then I have this times this. So I have plus 24 sine theta cosine squared of theta. And then plus 0 times 0, which is 0. So that's it. I have a total of 4 terms. Right? Everybody with me? Now let's see which ones I can say right away that are equal to 0. Sine theta between 0 and 2 pi. Antiderivative is going to be cosine theta between 0 and 2 pi. This is going to be 0. Does everybody agree? Does everybody understand why I'm doing this? Why I'm just crossing it out before even calculating it? Okay, this is important. Okay. What about sine theta times cosine theta? What is this the derivative of? Do you recognize it? It's going to be the derivative of, so sine, 2 sine theta cosine theta is sine of 2 theta. Do you know that? So this is sine of 2 theta, so it's the derivative of cosine of 2 theta up to some plus or minus or some scalar because of this. So do you see that this is the derivative of cosine of 2 theta? Between 0 and 2 pi, dies. Do you agree? Everybody? What's this the derivative of? Do you recognize? It's only if you're a bit, good at integrals. This is the derivative of cosine cubed, right? The derivative of cosine cubed is going to be 3 cosine squared times the inner derivative sine. So it's going to be this up to some scalar multiple, which doesn't make a difference. So cosine cubed, evaluated at 2 pi minus evaluated at 0, is again going to be 0. Now, if you're saying I'm never going to be able to see that this is a derivative of cosine cubed, I'm going to need to do a substitution in order to solve this, that's fine. It's just going to take you an extra line. That's no big deal. Okay? So I'm doing these shortcuts because I feel comfortable with it. But if you don't see it, then there's no reason to panic. It's just going to take an extra line. You're going to have to solve this. And after that extra line, you're going to figure out that it's 0. Everybody with me? Okay, so the only thing that really survives is this. So what we get is a minus 4, which I can pull out, and the integral from 0 to 2 pi of sine squared of theta. What's the integral from 0 to 2 pi of sine squared of theta? Pi. It's going to be pi, right? Because the answer is going to be minus 4 pi. But why is that true? So this is, again, a standard calc 1 integral. You need to use the formula for sine squared. Okay, so it's minus 4, the integral from 0 to 2 pi. And the formula for sine squared is 1 minus the cosine of 2 theta divided by 2. This is a standard not a standard trick, a standard trig formula And that's how you solve the integral of sine squared. Okay? Trigonometry. Okay, so what do we get? If we're at it, why not go all the way? This is 1/2 minus cosine of 2 pi over 2. The cosine of 2 pi part is its antiderivative is sine of 2 pi. That's going to vanish. Do you agree? So this is going to be 0. So what we get is minus 4 times 1/2 times 2 pi, which is the integral of theta from 0 to 2 pi, and this is just minus 4 pi. Good? Okay. So summary. This was long, and we used 3 solutions, and I think it's important. I mean, it's kind of a review. It was kind of a review problem, but it's a good time to introduce review problems because we're almost at the end of the course. Okay? So let's summarize what we did. Our original problem, we had a field, a surface, and we wanted to find the surface integral. Always you have the option of solution 1, calculate the surface integral. Parameterize the surface, find your field on the parametrization, dot the normal, that's the surface integral. Okay? Solution 2, standard, if you have an open surface, close it. Calculate the integral on the closed surface using Gauss. You just have to verify that your normal on all the components is pointing outwards. Using Gauss, you convert to a triple integral. In this specific example, the triple integral was right away 0. It was very easy because it was the divergence of a curl. In general, it's going to be a triple integral. You're going to need to calculate a triple integral. Okay? And then subtract the surface integral of the cap that you closed it with, which is usually going to be something two-dimensional and easy to calculate. Okay? This also works in general. Solution 3 was kind of unique for this example because in this example we wanted to calculate the integral of a rotor, not just of any given field, in which case you can convert by Stokes' theorem to a line integral over the boundary, over gamma, which is the boundary of the surface, okay, because it was the curl. Okay, and that's what we did. And by the way, you can play with these things even more. So we converted by Stokes' theorem to a line integral over the boundary gamma. You can take it a step further and say, okay, again by Stokes' theorem, I can convert back to a surface for which gamma is the boundary. But not necessarily this surface. I can choose any surface I want for which gamma is the boundary, and it's still going to hold by Stokes. So for example, you can do a surface integral of the disk. Gamma is the boundary of the disk as well. Do you see that? Okay, so I hope we'll have an opportunity to do some more examples, either together or you're going to do them on your own, and you'll see examples of that sort as well. And each of these solutions involves mastering the techniques, understanding what you're doing, what is change of variables, what is parametrization, how you solve a surface integral, how you solve a double integral, how you solve a triple integral, how you solve a line integral, and all of those things require practice. Exactly. Okay, so this wraps up this clip. What I want to do next is just a few comments on Stokes' theorem and how it helps us interpret the meaning of the rotor or of the curl. And for that, we're going to have to discuss one last topic in this course, which is conservative fields in R3, in three-dimensional space. It's going to be very, very, very similar to conservative fields in two dimensions. There's going to be one little twist to the plot, and we're very close to the end. Okay, so that's the end of this.